but it was difficult. It took me. I wasn't recovered until Saturday.
Yeah, I got back yesterday at 1:30 and was traveling for 3 hours.
Okay, 3 o'clock. Officially time to start class. And so, out of curiosity, how many people would be impressed if it's Wednesday's hump day, time to celebrate, and I take out a beer and put it in a pint glass and then just slam the whole thing down? Anybody be impressed?
I'd be impressed. Well,
What if instead of beer, I had it be bourbon? Would you be impressed then?
A whole bottle or a shot?
Pint glass.
Okay.
are you going to share that?
There's just me, myself. I'm very selfish.
So
You're not
why are
holding
we doing this? We're doing this because it's Wednesdays and it's hard.
I'm just asking a simple question. Would you be impressed?
Yeah.
Yeah? Why, which would impress you more, the beer or the bourbon?
Bourbon.
Why?
Alcohol content.
Alcohol content?
That's like funneling a beer and funneling vodka.
Where am I
Two
going
totally
with this?
different
Where am I going with this?
Concentration.
Yes. What is concentration?
Dosage.
Okay.
Amount over volume.
Yes, it is the amount. The amount over volume. Right? So bourbon, it depends on the bourbon, is about 40% alcohol. Beer, depending on the beer, is going to be somewhere between 0.5 to 6% alcohol. So it depends on the type of beer.
Did you say 0.5?
Yeah.
There's really beers that little?
Yeah.
Shit.
So like when they built the
Used to be.
pyramids, they gave the workers about a gallon of beer a day. That's what fed them. So you can get and like when like in Europe during the medieval times, the water was unsafe to drink. They drank beer. Like how were they drunk all the time? Because it's only like 0.5%. So it's like liquid bread. So you can get beer really, really mild. We like our beers a little more hearty now. So, but concentration is amount per volume. And so like if you go to the grocery store and you buy like, or if you look at, I like to look at labels and sometimes it says things like orange juice concentrate, right? You can buy orange juice concentrate. What is orange juice concentrate? Well, it's the whole flavor of a pitcher of orange juice contained in a little tube, right? So you got like something like a 200, 300 milliliter tube of orange juice goodness is the same thing as like 2 liters of orange juice, right? It's all that orange juice flavor concentrated. There's more of it per volume, more amount per volume. That's what concentrate means. That's what concentration is. It's how much stuff you have over the total volume. Oh, I guess I meant to mention, we're in chapter 5 now. So, surprise, surprise. And chemistry, we use a really weird type of concentration unit. We use something called molarity. And in colloquially, like around, like our everyday life, we typically use either parts per mass or parts per volume. And alcoholic beverages, it's parts per volume. So proof is double the alcohol percentage. So 80 proof is 80 divided by 2, 40%. And it's 40% by volume. So if you wanted to make your own vodka, at least by mixing liquids, you would make it, if you want 100 milliliters of vodka, you would take 40 milliliters of pure alcohol and 60 milliliters of water. And that would make the 40% or 80 proof vodka, if you will. So, okay, so molarity, concentration, amount per volume. Molarity is in moles per liter. Moles amount, something in moles, and liters volume. Also capital M for molar. These all mean the same thing. Molarity, molar, moles per liter, all the same thing. So for instance, if you wanted to make 1 molar hydrochloric acid, you would take 1 mole, which is 36.45 grams of hydrochloric acid, and put it in 1 liter of water. So that is 1 mole in 1 liter, 1 molar. You following? Okay, so let's do this for a problem. So what is the molarity of a solution that has 25.5 grams potassium bromide KBr dissolved in enough water to make 1.75 liters of solution. Okay, so the way we're going to solve this is the easiest way is dimensional analysis. Well, the most straightforward way. You can do this. If you want to do it in one step, go ahead. Figure out the number of moles divided by the liters. That's fine. You can go ahead and do that. I've been trying to train you to do dimensional analysis. And the way you do this, 25.5 grams KBr. And then we got to figure out how many grams KBr per mole KBr. And then last step, 1.7, just divide by 1.75 liters. 1.75 liters. So let me zoom in. So this is what we're going to go to get to moles per liter KBr. So I notice some people get confused about this sometimes, so let me can you see that? Okay, good, you can see this. So if you go to the periodic table, come on, focus. You there, the camera. There we go. Okay. So using the periodic table, oops, didn't mean to do that, meant to crop it. So to figure out for KBr, you have to look at the numbers in the bottom. So KBr, so it's 1 times 39.1 plus 1 times 79.9. And that's because there's one of each in KBr. And let's see here, that's 119. It's 119, and it's grams KBr per mole KBr. You probably, I know I gloss over this quite frequently, I get questions about this. So you understand this, right, where I'm getting it? So then we take this information to what we set up before, and this is 119 grams potassium bromide per mole potassium. Oh wait, I got it backwards.
Don't you want that on the bottom?
Yeah. Yes, units. All right. So now, if you look at the units, of course, grams KBr cancel, and we're left with moles KBr over liters, and this also equals molar, capital M. So capital M is moles per liter, and put that in our handy dandy calculator. What's my advertisement going to be today with my free calculator? Let's see, 25.5 divided by 119 divided by 1.75. Oh, no ad. All right. Oh, here we spoke too soon. Uber is my ad for today. 0.122 moles KBr per liter, and just to give you guys the complete experience. So if you're wondering how I set class up, I do it this way. Taking pictures. Like so. Okay. All right, so recap, we have 25.5 grams potassium bromide dissolved in 1.75 liters. What's the molarity? Well, we set this problem up by starting off with what we want on the left, or I'm sorry, what we have on the left, and we're moving towards the moles per liter. And with dimensional analysis, making sure the units work correctly. You have moles on the top and liters on the bottom here, and then the grams are going to cancel. So that's part of your strategy, is to get the units working correctly. And so 25.5 divided by the molecular weight of potassium bromide, you figure that out from the periodic table. And then multiplying and adding the proper terms is 1 potassium, 1 bromine. So it's 39.9 for potassium, 79.1 for bromine, and then you add them together for 119 grams per mole. And in this case, you divide by it, you make the units work out, and then you get the 0.122 moles per liter, or molar. Questions with this? Yes.
So nothing goes on top. Is there a 1?
No,
on top
well,
of
it's
1.5, or-
sure you can put a 1 there if you want.
Okay, just to fill the spot.
Yeah,
Okay.
it makes you feel better.
It does.
Okay. So, other questions? Okay. All right. So another problem. So this chapter is about aqueous solutions. So that's the main focus of this chapter. Aqueous means water. So a lot of the solutions we're talking about with water. And there's a shortcut for doing dilution. So for doing dilution maneuvers, there's a shortcut, and the shortcut is M1V1 equals M2V2. So moles of one, molarity of one, volume of one equals the molarity of two, volume of two. Sometimes people do C1V1 equals C2V2. That's the concentration of one times the volume of one equals the concentration of two, volume of two. Really, any concentration units work, any volume units work, as long as you're consistent. So it doesn't have to be moles per liter in liters. So you can really use any concentration units you want. You can do it percents and so on. So, but let me do it for this problem. So we need, we're going to dilute 0.2 liters of 15 molar sodium hydroxide to make a 3 molar solution. So do the M1V1 equals M2V2. Molarity of 1 is 15.0 molar. Volume of 1 is 0.200 liters equals 3.00. And then our unknown, I'm just using an X. I like X for my unknown. So one equation, one unknown. So we're going to solve for X. So 15 times 0.2 divided by 3 equals X. So 15 divided by 3 is 5 times 0.2 is 1. X equals 1.00. It's what volume? It's 1 liter. So that means that if you have 200 milliliters, 0.2 liters of that solution, you put it into a 1 liter volumetric flask and you fill the rest up with water. So that's how you would dilute this. So recap, we have this equation, molarity of 1 times volume 1 equals molarity of 2, volume of 2, and we're given 15 molar 0.2 liters, and we want to know the volume it takes for 3 liters. So we put in the equation, put in our unknown, solve for the unknown, 1 liter. Questions with this? Okay. So these are decimal points. Because I know it's so hard to see in this class. The screen kind of sucks. But 50 milliliters of 0.5 molar solution will make what concentration if you dilute it to 200 milliliters? And the M1V1 equals M2V2. So how many people think A, 0.125 molar? How many think B, quarter molar, 0.25? How many think C, half molar? I think D, 2 molar. All right, so we'll come around. Is anyone stuck? Raise your hand. No one's stuck. Okay, just need more time. Zero, zero. Looks like everyone's getting it. Is anyone not getting an A? So yes, answer is 1/8 or 0.125 molar, eighth molar. So I think this is pretty straightforward. Does anybody want it re-explained? Okay. All right. So this chapter is called Aqueous Solutions. So we should probably talk about what a solution is. A solution is a homogeneous mixture. Homogeneous, homogeneous, however you want to say it. Uniform. Homo means uniform. So uniform mixture. And specifically we're talking about aqueous solutions. So air is a solution. It's a homogeneous mixture. It's made of gases. And there are solid solutions. So 14 karat gold, 10 karat gold, 18 karat gold, those are solutions too. So they're solid solutions. They're made of copper, silver, and gold. And they're uniform. And there's a lot of aqueous solutions, and aqueous solutions are important for two reasons. Number one, the Earth is about 2/3 covered in water, so there's lots of solutions on Earth. Another thing is biological creatures are very heavily aqueous solutions. So our blood plasma and our cytoplasm, they're solutions. So homogeneous mixtures. And some terminology. So solvent means whatever you have the most of. It's what does the dissolving. And solute is the least. It is what is dissolved. So sometimes you'll see these things that say it's solvent-free. Like this paint thinner is solvent-free. There is no such thing. It's probably means it has no hydrocarbons in it. So it's something else. But saying a solution is solvent-free is it's completely wrong. Like I said, usually it means that doesn't have any sort of hydrocarbons in it. So, for instance, with solutions, ocean water, the ocean water it depends on where you're at, but on average, the ocean is about 96.5% water and about 3.5% salts. Predominantly for the salt is sodium chloride, but it has other stuff in it too. So that's what ocean water is. Does anybody know what the human body's blood plasma and cytoplasm is in terms of salt concentration? Also the same concentration of IV bags. It's 0.9% sodium chloride salt. So for we humans, we don't have very efficient kidneys, so we have to drink fresh water. Fresh water is defined as less than 0.9% salt, because then we can get hydration from it. So there are other creatures that can drink salt water and are fine. They can get hydrated from it. Sea otters, for instance. So sea otters are really good at taking in salty water. So they don't need to drink fresh water. We, on the other hand, if we drink ocean water, it's just going to make us thirstier. So it doesn't work very well. And some other things with solutions. So we're talking about types of solutions. Whenever I see this, I always think of the movie Idiocracy. Has anyone ever seen Idiocracy? Yeah, yeah. So it's a post-apocalyptic movie that's kind of funny. Okay, so some types of aqueous solutions. So we're kind of breaking aqueous solutions down into different categories, and here's one of the ways we can break them down. So we can have strong electrolyte, weak electrolyte, and non-electrolyte. So water, pure water, is considered to be a non-electrolyte. So water, pure water, does not conduct electricity very well. It does a really tiny bit, but not very well at all. And a strong electrolyte, so what does electrolyte means? It means it can conduct electricity. So an electrolytic solution conducts electricity. So when you see things like sports drinks, it says contains electrolytes, it means it can conduct electricity. And our body needs electrolytes. We need them for various functions. So our nerve cells, for instance. So we do need electrolytes. They're nutrients. So that's really all it says. When you see it contains electrolytes in like Gatorade, it just has salt. It's glucose sugar or dextrose sugar, same sugar, and salt. So if you want to make your own Gatorade, buy some glucose, buy some salt, and you've made yourself. Chemically, it's the same thing. So
What kind of salt?
what's that?
What kind of salt? Like
Sodium
sea
chloride.
Salt, table salt.
Yeah, just it would be kosher salt, because that's just plain sodium chloride. So if you buy salt in the grocery store, it usually is iodized. So they don't use iodized salt in Gatorade and most sports drinks. Okay, so strong electrolytes means that water solution will conduct very well. Weak electrolyte means it conducts a little bit. Non-electrolyte means it doesn't conduct. So, and I can tell you the reason why I'm here, among other things, is because pure water or fresh water is not a very good conductor of electricity. My grandmother, when she was a child, she was swimming in a lake, a small lake, and it got struck by lightning while she was in the lake. She was swimming, and she said it just felt kind of like a bzzz. She felt a little bit of a shock, but it wasn't enough to defibrillate her. And a bolt of lightning has about on the order of 1,000 amps and 100,000 to 1,000,000 volts of potential. So there's a lot of energy on a bolt of lightning. So in that little tiny lake, the water did not have enough conductivity to defibrillate her. So it doesn't take that much to defibrillate someone. But it wasn't enough to really, she didn't even feel it that much. So again, I don't recommend that you go swimming in lakes while there's an electrical storm. But obviously, since I'm here, this is my question.
Would it be a different story if it was strong with it was just like salt water?
Oh yeah.
It's like the ocean.
Well, the ocean is
ocean's
pretty
too big.
vast, right? I mean, the ocean and lightning is striking
Like
the
a
ocean.
saltwater pool.
Yeah, saltwater
But
pool.
like you get, if like a bolt of lightning strikes near you while you're in the ocean, then
Yeah, then you're in trouble.
yeah,
But I
What kind
mean,
of fish don't fry.
they do, don't they?
yeah, they can.
Yeah.
And it can melt sand too. Like if it hits the
Yeah.
beach.
Yeah, what's that movie? Sweet Home Alabama.
Yep. Mhm.
Yeah. Aw.
All right. So let's talk about this. So, all right, so here is salt. So sodium chloride salt is an example of a strong electrolyte. So, and so why does salt dissolve in water? Why does it even dissolve in water? Well, here's the ionic network of salt, and you have the positive. It's probably sodium chloride, but I'll just use sodium chloride as an example. It's not labeled, but the positive sodium ions here in purple, and the larger negative chloride anions. And the reason why it forms a structure is that the unlike charges attract, right? So the positive cations are attracted to the negative anions. And it forms a structure so it's close as it can be to the opposite charge and far away from the same charge. So water, we haven't talked about water yet, but water is known as a polar molecule, and which means that there is a slight negative charge on one end, the oxygen end in this case in water. There's a slight positive charge on the hydrogen end of the water. And if you see here that the water, 6 waters are surrounding one of the sodium ions, and 6 waters are surrounding one of the chloride anions. There's 7?
Yeah.
Oh, you're right. There is 7. It should be 6. Oh well. Good call. I can count. Okay, but I guess the structure would be different. That would be okay. Well, this is an octahedron. If that is indeed 7, that would be a pentagonal bipyramid. So the structure, I guess that could happen, but it's usually 6. So most of the time, you get like an ion, and then you get an octahedron. So that means that you have waters all form around like this. So an octahedron. Let's see here. I guess I can shake an octahedron. Hopefully I haven't looked at anything embarrassing. Okay, no, good. Whew. You can see what I've been Googling. Oop. No, you don't want to see my inbox. There we go. Here's an octahedron. So this is usually what the structure forms. It's either an octahedron or a tetrahedron, so it's usually 4 or 8. It could be 5. So an octahedron has a square in the base. If it was 7, there would be a pentagon on the base, and then one above and below. But the idea here is the reason why salt dissolves in water is that there's 6 water molecules surrounding this, 6 or 7 depending on the ion, I guess, around this. But the idea is that this 13 charges is greater than just the 2 in the structure. So that way it can pull the whole thing out in a solution. And later on today, we're going to talk about solubility, whether or not things will dissolve. And the things that can dissolve are almost always they're +1, -1. So the really small charges. The big charges, they're not soluble. They're too strongly bound. They can't dissolve in water. So, okay, so now we have these charged particles in solution. And since there's charged particles in solution, this can carry electrical current. So electric current can travel through this solution here. And let's compare it to a non-electrolyte. Here's sugar. So here's sugar water. And sugar water, there's no charged particles here. So since there's no charged particles, there's no way that electricity can travel through that. Now, let's compare this to life. So and talk about relationships. So sodium chloride. So sodium chloride salt. A strong electrolyte is kind of like someone you just met that you're sharing a ride with. You ever taken Uber shared before? So imagine you're doing like an Uber share and you're going to a place and you get to like, say you're taking the Uber share to the beach and you're like, all right, we shared our Uber. Like, all right, nice to meet you. I'm going this way and you're going that way. All right, see you later. Have a nice life. Right? So that's a strong electrolyte. They go somewhere, they get in water, and they fly apart. Like, we don't care about each other anymore. You're gone. You're dead to me. So a weak electrolyte is like a disgusting couple in love. So like if a couple in love comes to a place, what happens? They arrive, and what do? They're hanging out together. They're holding hands. What happens? Well, one of them has to go to the bathroom. So what happens? Well, the other person's just waiting here by the bathroom. Person goes to the bathroom, and what happens when the person comes out? They're holding hands again. They're walking around, right? They're always together except for a little bit of time. Maybe at home they're hanging out together on the couch, and then one of them has to go take a shower. The other person's still on the couch. But usually they're just disgustingly hanging out together. That's a weak electrolyte. So they really spend a lot of time together, but then every once in a while they separate a little bit, but as soon as they can get back together, they do. That's a weak electrolyte. So here's an example of one, but even this, here is acetic acid. And if you can see this, it's together here. This is acetic acid. It's together here. It's together here. Oh, this one's a little ionized. But it'll get back together as fast as it can. So acetic acid, even this is kind of overblown. Acetic acid, depending on the concentration, is usually together about 98, 99% of the time. So what are weak electrolytes? They tend to be weak acids and weak bases. We're not going to talk too much. We're going to talk about acids and bases next class, but we're going to go much more in depth into it next semester. So just because, you know, chemistry, I know in the beginning we cover so many different topics really quickly. So it's a weak acid, weak base, this case weak acid. So non-electrolyte, and you'll do this in lab. You put it into, you have the electrodes, see if the bulb lights up. Non-electrolyte doesn't light up. Strong electrolyte, the bulb is really bright. Weak electrolyte, you can see it's on a little bit, but not that much. So remember, you need ions to transfer electricity. So the strong electrolyte, they get to somewhere, they break apart, and they want nothing to do with each other. Weak electrolytes, though, they're sappy in love. They want to stay together as much as they can. Every once in a while, they break apart, and when they do, they conduct electricity, but they get back together as fast as they can. So that's the weak electrolyte. So, questions? Again.
So this might be already obvious, but so like strong acids and bases are strong electrolytes. So like on each side of the scale.
Yeah.
Like acid and bases. And then when you get like closer to the middle, like neutral.
Yeah.
No electrolytes, right? Or no?
So, simple answer is yes. It's complicated because, like, depending on some of the molecules. So, methanol, for instance, is considered a non-electrolyte in water, but it's also weakly acidic. But water itself is more acidic, and sugar is not acidic at all. So, well, actually, I'm trying to complicate it. Simple answer is yes. I'll stop there. Okay. Other questions? All right. So, which aqueous solution conducts electricity? So we have an ionic compound, we have sugar, and we have methanol. So which one conducts electricity? It is the ionic compound, because it would break apart to form different ions. And this one actually ends up being soluble. We're going to learn about solubility in a very quick moment. But how do you know, just looking at this, which one is going to be soluble, which one's going to be a strong electrolyte, and which one's going to be a non-electrolyte? For you at this level, it's because these contain only nonmetals, and this has a metal and a nonmetal. That's how you can tell right now. Is it more complicated? Of course. You know, can you have nonmetals be strong electrolytes? Yes, because if you have something like ammonium nitrate, so these are two polyatomic ions, and these will break apart to form ammonium plus ions and nitrate minus 1 ions, and this will conduct electricity. I know it's all nonmetals, but I was looking through the book and all the problems. At this level can go with the fact that this has a metal in it and those don't. So, questions with this? Okay. All right. As promised, we're going to talk about why stuff dissolves in water. And from what I hear, I've never taken the MCAT, but I guess they put some of these questions on the MCAT because it speaks specifically to logic. So these are about logic, about reading charts and what they mean. So on the top here, we have compounds that have the following ions are generally soluble. So remember what I said before. Things that are soluble are the ones that have the low charges. And later on you'll learn these are also the big ones too, the little tiny charge with the big ions. The alkalis have big ions, for instance, and so do the halides. So the alkali metals, lithium, sodium, potassium, will be rubidium, cesium as well. But lithium, sodium, potassium, and ammonium, these are always soluble, no exceptions. So nitrate and acetate, so these anions are always soluble, no exceptions. Chloride, bromide, iodide, these tend to be soluble with these exceptions, silver, mercury, and lead. So if one of these combines with these, then it's insoluble, but everything else is soluble. And sulfate is soluble with the exception of the alkaline earths, lead and silver. So these tend to be soluble except for these things. So if you want a colloquial example, it's like, say, the days of the week. So every day I eat breakfast. No exceptions. I eat breakfast every day. On Saturday and Sunday, I sleep in. Today is Wednesday. Did I sleep in today? No. So I do not sleep in except for Saturday and Sunday. So that's the exception. So chlorides tend to be soluble unless it's combined with silver, mercury, or lead. So that's the idea. So we have a rule and then we have an exception to the rule, which is probably you've learned is what general chemistry is. It's really logical, but there's a rule, there's an exception to the rule, and sometimes there are exceptions to the exceptions, and other times there's some exceptions to those exceptions, under certain circumstances, of course. Which is why everyone loves chemistry. Actually, it's kind of fun. If you study it for years and years and are raised with it and have a family history of it, there's actually an intuition about it.
There's a chemistry.
Yes, there is. So, all right. Now we talked about what's soluble. Let's talk about what's insoluble. Insoluble means not soluble. So hydroxide and sulfides are insoluble with the exception of alkalis and ammonium because they're always soluble. And sulfides are insoluble with the exception of the alkaline earths. And hydroxides are insoluble with the exception of the alkaline earths, although I don't necessarily believe this as much because, I mean, you can, like calcium hydroxide, you can drink it. If you drink sodium hydroxide, you're going to the hospital. If you drink calcium hydroxide, though, it can smooth your upset stomach. So, okay, carbonates and phosphates. So notice that these are bigger charges. Also, sulfides, bigger charges. We're getting bigger charges now. These tend to be insoluble, not soluble, with the exception of the alkalis and ammonium, because those are always soluble. All right, so those are the rules there. Okay. Now let's apply this to, I guess I should just write them. It's easier to do if I write them up here. So lead chloride, copper chloride, calcium nitrate, and barium sulfate. Is that all in? Yeah, okay. So the next part here, are these compounds soluble? So lead chloride. So chlorides tend to be soluble except lead plus 2. And because of this, yeah, this is not soluble. I'll give it the I. This is insoluble. And how do you know this is lead plus 2? Chlorides are -1, and there's 2 of them here. So 2 -1s. So for this whole thing to be not charged, that means lead needs to be plus 2. If it was lead 4 chloride, or PbCl4, that would mean that this was plus 4. But since there's 2 -1s here, this one's plus 2. So, but right now for your analysis, chlorides here tend to be soluble with the exception of lead plus 2. So questions with this one? Okay, copper chloride, same thing. Chloride's going to be soluble. Copper is not one of the exceptions. Therefore, copper chloride is soluble. I'm giving an S for soluble. Calcium nitrate, and remember these parentheses, this means that there's 2 of these nitrates here, and calcium here. So all nitrates are soluble, no exceptions. That is definitely soluble. And sulfate tends to be soluble. Barium is an exception. Therefore, barium sulfate is not soluble. So, questions with this? And I can tell you barium sulfate tastes terrible. Have you ever gotten a CT scan with the contrast? Am I the only lucky person that had to do that? So I had a couple students in the morning class. If they ever want to take an x-ray of your gut, a CT scan is just a series of x-rays. They make you drink barium sulfate. And man, that stuff tastes terrible. Ugh. No matter how much they flavor it, it still tastes terrible. Okay. All right. Any questions before we keep on going?
Yeah, fluoride.
Next thing we're talking about are precipitation reactions. So you're going to do a whole lab on this, although you're going to do drops of it. In your lab, you're going to see a cloudy solution. And the idea is you're going to have two solutions. So they're usually clear. You have two solutions, and you mix them together. So you take one solution, you mix them together, and then what can happen sometimes is a new compound is formed. So a new compound is formed that's not soluble in water. And then that will fall to the bottom of the solution. So that's what a precipitate is when you mix two solutions together and a solid forms and sinks to the bottom. So precipitate. There are other types of solutions. Sometimes you mix them together and you can get what was formed a supplicant. That's a solid that floats at the top. That's a supplicant. And on Monday, we'll talk about gas evolution reactions. Sometimes you take two solutions, you mix them together, and it forms a gas. So in old textbooks, so if you go by old textbooks, we indicate it with the solid. So S for, I know I use S for solubility, S for solid. In old textbooks, in some countries, they put a down arrow. So I know, so we used to do this in the United States. We would indicate a precipitate with a down arrow. We would indicate a gas evolution reaction with an up arrow. And they still do that in Vietnam. Because I had a Vietnamese student that came and told me, like, oh yeah, that's how we do it in Vietnam. We have a down arrow for precipitate and an up arrow for gas evolution. So she obviously had chemistry before she had me. But, okay, so a precipitation reaction. You have two solutions here, and in this case, it's hard to see, it's fuzzy. This is potassium iodide. So we have the silver potassium ions and the purple iodide anions. So potassium iodide, all potassium salts are soluble. So that's soluble. Lead nitrate, all nitrate salts are soluble. So we have the yellow lead, and then we have this red and black sort of pinwheel as the nitrate anions. So all nitrate anions are soluble. So all potassium salts are soluble, all nitrate salts are soluble. So these are definitely soluble. But when you mix something into solution, if you can kind of see this, the ions are flying around. They're not just sitting there. When they're in water, they're flying around. They're bumping into each other. And what can happen is, or what does happen is, the lead, oh, you can't see that at all. Jeez. What can happen when you mix these together is the lead ions will bump into the iodine ions, and the problem is lead iodide is insoluble. It forms a solid. So from that, the lead and the iodine get together, and then they form a solid, and then they fall out of solution. The lead iodide does not dissolve. And then it forms a precipitate, and it falls to the bottom of the solution. So, and to describe this, and I'm from my teaching evaluations suggested I say this, and so I want to say, please pardon the heteronormality of this, but it's easy to explain this way. And actually, these types of of reactions are referred to as partner exchange reactions. But it's easy to explain it that way. So pardon the heteronormality of this. I know other couplings are possible, but I'm just calling the cations like males and the anions like females. And the reason why they bond together is because they're unlike charges. So, and this works all the time for charges. Like charges repel, unlike charges attract, always. Unlike people. I know people have different ideas, but it's a partner exchange. So when you have two salts in different solutions come together, they can undergo what's known as a partner exchange reaction. And the question is, in these partner exchange reactions, is one or more of the possibility of the couplings, is one or more of these create an insoluble compound? If it does create an insoluble compound, then a precipitation reaction will happen. If these coupling are not possible, nothing happens. Absolutely nothing happens. So let's look at this one here. So potassium carbonate and nickel chloride. So if you remember the rules, potassium, and you don't have to memorize the rules, by the way. You do not have to memorize them. I have it memorized, but because I'm a doctor of chemistry. So you will be provided with any chart. So potassium carbonate, all potassium salts are soluble. Nickel chloride, chloride is soluble with the exception of mercury, silver, and lead. So nickel is not one of those, therefore it's soluble. So these are both soluble, and that's also why we have this AQ. AQ means aqueous. It means it's dissolved in water. And the possible coupling with this is, I like blue better. So the possible coupling with this, what is the aqueous? The possible, and remember, so we're going to have potassium as a cation, and we have the two cations and nickel. So potassium can form potassium chloride, and nickel can form then with the carbonate. So remember, the positives will not mix with the positives, the negatives will not mix with the negatives. Only the positives and the negatives, the unlike charges, will attract, not the same charges. So let's balance the charges here. You can know this a few ways. Carbonate is a polyatomic ion, and you'll be given a chart, and carbonate has a charge of -2. You can know it that way. Or you can know that potassium is an alkali. These are +1s, and since you have 2 + 1, that forces this to be -2. Same thing with nickel chloride. Nickel, what's the charge of nickel? Chloride is -1. There's 2 of them, so nickel is +2. So, and now when we look at the number of atoms for each, potassium chloride is +1 -1, and nickel carbonate is +2 -2. Therefore, we don't need to add any numbers in front with any subscripts anywhere. Okay, so balancing the chemical equation now. We have 2 potassiums here. Multiply it by 2 to get 2 potassiums there. 2 chlorides here. There's 2 chlorides there. 1 nickel there. 1 nickel there. 1 carbonate here. 1 carbonate there. So it's balanced. Now we have to look to the rules to see, is one of these soluble or insoluble? So potassium chloride, all potassium salts are soluble. So that's aqueous. And then aqueous means it's dissolved in solution. Now we look at nickel carbonate, and the rule of carbonates. Carbonates are insoluble with these exceptions, alkalis and ammonium. Is nickel an alkali? No, nickel is not an alkali. Therefore, nickel carbonate is a solid, and it drops out of solution. So in an old textbook, you would see a down arrow. So, all right, so you mix these together. You look to see, okay, potassium's going to mix with chlorine, and nickel's going to mix with carbonate. Is one of those going to be insoluble? The nickel carbonate is not soluble, it's insoluble. It will form a precipitate, so you write the reaction that way. Questions with this? No. Okay. Next one. So we have sodium nitrate and lithium. I should put the aqueous. Lithium sulfate. So we're going to mix these together. What are the possible couplings? This is lithium 2. So we can have lithium nitrate and sodium sulfate. So let's look at the charges. Sodium's +1, nitrate, if you didn't know, it's -1. So +1, -1. So lithium is +1, that means sulfate is -2. Or you'll be given a chart that has -2. Are you stretching or you have a question?
No, I have a question. How do you know what the charge is?
Okay, so if you look at the periodic table, these tend to be +1, these are +2, and these are -1 because they're 1 away from here, and the +1s are 1 of that, and the +2s are 2 from the noble gases. So the alkali metals, they're +1 in their compounds. So since this is +1, nitrate is -1. Or you'll be given a chart that says nitrate, nitrate's going to list it as -1. Same thing with sulfate, sulfate is -2. So lithium is +1, nitrate is -1. This is left as is. Sulfate is -2, sodium is +1. So we need to put a 2 there underneath the sodium. So we need, that's a 2. There's 2 +1s to counteract the -2. And now we balance the chemical equation. 1 sodium here, 2 sodiums there. Put a 2 there. 2 lithiums here. 2 lithiums there. And now look at the sulfates. 1 sulfate here, 1 sulfate there. 2 nitrates, 2 nitrates. It's balanced. Okay. Now let's go to the rules. Is lithium nitrate, is this soluble? All alkali salts are soluble. All nitrates are soluble. This is definitely soluble. And then sodium sulfate, all alkali salts, sodium is an alkali, all alkali salts are soluble. Therefore, both of these are soluble. Oop, that's a Q. AQ. That means that this is no reaction. So you sat there, you took 2 beakers, you poured one in the other, like, ooh, precipitate happened. What does this one do? You pour it together, absolutely nothing happened. You know, you're expecting something to happen, nothing happened. No reaction. So, questions with this? Does everybody see the logic and how I'm doing this? Okay. Copper chloride in solution mixes with lead nitrates. What are we making? What are we making in this? And what I'm going to do is I'm going to copy this and bring this up. Let me do this. It's so hard to read this stuff on the screen here. Let me copy this whole thing. And then bring it up here. This. If you can read this. So we have copper chloride and lead nitrate. Those are both soluble. What, if any, precipitate are we going to make? Are we going to make copper nitrate, lead chloride, dichloride nitrate, or no reaction? So who's going to mix with whom? So copper is a +2 ion. They're both +2 ions, copper and lead. So copper is +2 and lead is +2. Well, two +2 ions, will they mix together? No. They're the same charge. They repel. Chloride is a -1. Nitrate is a -1. Will a -1 mix with another -1? No. That means, oops, didn't mean to erase it. That means that one's out. So A and B are the only possibility where you have a cation and an anion, a plus and a minus ion, or nothing happens. How many think A, we form copper nitrate precipitate? How many think B, we make lead chloride? How many think D, no reaction? So we got some for A, some for B, and no one thinks no reaction. I'll go ahead and tell you it's not no reaction. So it's not D. So let me come around and see what you're thinking. Yeah, so it'd just be, yeah, you voted for A.
So this would be a solution, this would be the solid.
The lead chloride would be solid.
Yeah,
This would be aqueous. Yeah.
Yeah, that's what.
Yeah. Okay. Okay.
That's,
They're asking for what the salt.
Yeah,
so
what was
we're
made?
asking for solid or?
Yeah.
Okay.
A is wrong.
Okay.
Wouldn't it be better to ask what's solid to specify what?
Sure. Let's
Because it makes both, right? Just one is.
Well, this is an aqueous. I mean, it's not solid. It's
Yeah. So, what doesn't it technically make the solution then?
Yeah, but a solution is aqueous.
So we're looking for a solid.
Yes.
Okay. Might have missed that part.
Okay. Well, no worries. You're on my online Zoom.
Yes.
Okay. Well, welcome. Do you have any questions? Are you following?
Yeah, I'm following. I'm a chapter behind this.
Okay. Well, good.
That's okay. That's all good, man.
So what are you thinking?
Why was we talking? So.
Yeah.
Yeah, no, that's obviously it's salt because it's insoluble.
Yeah. Okay. Cool. Yeah. Same sense as chloride, and then the lead is exception. Oh, it's hard to see that here. Jeez. Here, don't look at those classroom. Are you guys following? So these seem to be soluble, chlorides seem to be soluble, but lead is an exception. Therefore, that one is insoluble. So copper nitrate, nitrates, so the nitrates are right here. Nitrates are insoluble. So this one, A is soluble. B, it's a chloride, and lead is an exception. Therefore, this one does form a solid. Yeah. Jeez, need to equalize. See this stuff. Okay, that's gonna be following. So the idea here is, so for nitrates, all nitrates are soluble, so this is soluble. But the lead chlorides tend to be soluble, but lead is an exception. Therefore, this one forms a crystal. You get that, or? Are you going? There you go. Okay. Where are you confused? So do you understand that calcium nitrate
So I said that I sleep in on Saturday and Sundays, every other day I get up to 6. So today is Wednesday, that I sleep in, I get up at 6. Right? If it was Saturday though, my day off, I sleep in. That's the exception to getting up at 6. This is soluble, but that's an exception. Therefore, this is not. Is that any comments? Okay. This is no reaction. This means nothing happens. So something does happen. So it's not that. So the chloride and nitrate. So chloride is -1 and nitrate is -1. 2 negative charges won't couple. Because so have you ever played with magnets before? Right? You can only like when you get the same end of the magnet, they repel. Right? You try to play with them, they stay apart. So same idea. The negatives, you try to put them together, they fly apart. But positive and negative, they attract. So you have to have dissimilar charges, ones that attract, the same charges repel. So the 2 anions, and it's even in the wrong ratios, it would be, but anyways, this would not form because it's just the negative ion won't stay together. It's not really off. Do you have any questions? You following? Do you have any questions? You guys doing right? Do you have any questions? You got that? Are you following? Okay. Go ahead. What are you doing? Okay, you got it? Okay, yeah.
All right, everyone is converging. It is in fact B. That is the right answer. Okay. Anybody have any questions? And once again, this class is done faster than but because I care about your education, I have prepared extra material for you. But I mean, I'm just going to go over more problems. So you are free to go if you want to get out of here. I am not going to stop you. But yeah, it's funny that.
Are you doing more aqueous solutions?
Yes,
Okay.
yes I am. And where did I get this? Wait, this is the right chapter? Chapter 4, I got the wrong chapter.
But because we care about education, stay.
Of course you care. Oh, that's fuzzy. It's not focusing. Focus, focus. There we go.
I was gonna say that looks like a good one.
Nothing like comparing. You're welcome. All right. Current problem. A 25 milliliter sample of 1.2 molar potassium chloride is mixed with 15 milliliters of 0.9 molar lead-2 nitrate solution, and a precipitation reaction occurs as follows. The solid lead chloride is collected, dried, and found to have a mass of 2.45 grams. Determine the limiting reagent, theoretical yield, and percent yield. So good stuff from last class. So this is a limiting reagent problem. And so we have to figure out what the limiting reagent, theoretical yield, and percent yield is. So let's see here. We'll start with potassium chloride. 1.2 moles KCl per liter times 0.025 liters. Do you want me to turn milliliters into liters, or are you fine with me skipping that step and just writing in liters? Raise your hand if you want me to write out the steps. Okay, all right. "25 milliliters times liter to 1,000 milliliters." So, and look where we're going. We are now, we have, from this, we're getting rid of the milliliters and liters. So the milliliters and the liters cancel. Unit-wise, we're at moles KCl. So keeping track of our units, we're at moles KCl. Now we have to go to moles lead chloride, and there is a mole lead chloride to 2 moles KCl. So we know this from the 2-to-1 molar ratio. You can't see that as well. Shoot. The 2-to-1 molar ratio in the balanced chemical equation, because you need 2 moles of KCl for every 1 mole of lead chloride. And then we got to figure out the mass of lead chloride. 35.4, that's 70.9. 70.9 plus lead. Lead, I think it's 200 and something. Lead is 207.2. 207.2. So that means there are 278.1 grams lead chloride per mole lead chloride.
How did you get that 278?
So lead is 207.2.
Okay.
So
Oh, here.
lead is right here, 207.2.
Plus.
Chlorine is 35.45. 35.45 times 2 is 70.9 plus 207.2. That'll be 278.1. Am I doing that math in my head correctly? I think so. At least I hope so. Okay. So we got to see what that is. We'll do that in a second. And then we have, so 15 milliliters of 0.9 molar lead nitrate. So same idea. I'll do this in red. I'll do it with blue. I like blue better. So 0.9 moles PbNO3 per liter. We have 15 milliliters, so 15 milliliters, liters to 1,000. And then the ratio is going to be 1 mole lead chloride per mole lead nitrate. As in the 1-to-1 ratio in the balanced chemical equation, then 278.1 grams lead chloride per mole lead chloride. And let us do both in our calculators. So 1.2 times 25 divided by 1,000 divided by 2 times 278.1, and we get 4.17, and the other one is going to be 0.9, oops, that's too many nines, times 15 divided by 1,000 times 278.1. And this is 3.75. Okay, so that means that this is the limiting reagent and theoretical yield. So now we got the percent yield. It's going to be their actual yield, 2.45 all over 3.75. So 2.45 divided by 3.75 times 100%, and we get 65.3% yield from this. So, all right, recap. What?
I'm sorry, where does the 15 milliliter come from?
Right here.
Oh, perfect. Okay.
All right, so we're given two solutions and a balanced chemical equation, and we got to figure out what the theoretical yield is, and we're given an actual yield to figure out the percent yield. So using the concentration and volume of the solutions, we figure out the moles of each of the reactants, and then we look at the stoichiometric ratios to figure out how much product that we can get. So we find out that the limiting reagent is the lead nitrate, and then we're supposed to get 3.75 grams as a theoretical yield. We only get 2.45, which means we get a 65.3% actual yield from this chemical reaction. So, questions with this? Nope, and I think that we got 2 minutes left. It's not really worth starting a new problem.
The theoretical yield is
The-
3.75.
Yeah, that's the most that we can get from this.
And then the other one was the LR,
This is the actual yield.
actual yield,
Yeah, it's found to have
which
a mass.
is given to you in the
Yeah.
equation. Okay.
And not in the equation, but in the problem.
In the problem.
Right here. So, no questions? Okay. All right then. Well, thank you for staying and watching me